In the previous lesson, we worked with the quotient ring Z7 bracket x mod the ideal bracket x squared minus 1, which contains cosets of the form a of x plus bracket x squared minus 1, where a of x is a polynomial with coefficients in Z7. And here's our opening question. Is this quotient ring a field? Why or why not? So please pause the video and work on this problem, and we will go over it shortly. The answer is no, because our quotient ring has 0 divisors. And to see that, let's multiply the cosets x plus 1 plus bracket x squared minus 1 and x minus 1 plus bracket x squared minus 1. Now, neither of these two cosets is the 0 coset, and that's because the coset representatives, x plus 1 and x minus 1, are not multiples of x squared minus 1. So to multiply these cosets, we can just multiply their coset representatives. And so we get the product x plus 1 times x minus 1 plus bracket x squared minus 1. But x plus 1 times x minus 1, this product is equal to x squared minus 1. And so we get x squared minus 1 plus bracket x squared minus 1, which is equal to the 0 coset, namely 0 plus bracket x squared minus 1. So we have a pair of non-zero cosets of the quotient ring that multiply together to the 0 coset, which means that these cosets are 0 divisors of the quotient ring. And the key here is that we created these 0 divisors using the factorization of x squared minus 1, which is x plus 1 times x minus 1. This observation leads to the following implication. If x squared minus 1 is factorable in Z7 bracket x, then the quotient ring Z7 bracket x mod the ideal bracket x squared minus 1 is not a field because it has 0 divisors. And the generalization of this was proved in the previous lesson. In today's lesson, we will work with the polynomial ring R bracket x, where R is the field of real numbers, and bracket x squared plus 1, or the principal ideal generated by x squared plus 1, which is the set of all multiples of x squared plus 1. Now the quotient ring R bracket x mod the ideal bracket x squared plus 1 contains cosets of the form a of x plus bracket x squared plus 1, where a of x is a polynomial in R bracket x. Now, unlike the example in our opening question, the polynomial x squared plus 1 is unfactorable in R bracket x. So what would that say about our quotient ring? That's one of the key ideas of today's lesson. Now please pause the video and work on day 34 classwork. And afterwards, we will discuss some of the problems and concepts. Today, we worked with the polynomial g of x, which equals x squared plus 1. And the key here is that g of x is unfactorable in R bracket x. We found that the distinct elements of our quotient ring, R bracket x mod the ideal bracket g of x, are cosets of the form a plus bx plus bracket g of x, where the coefficients a and b are real numbers. We then found an isomorphism between the complex number c and our quotient ring, where the complex number a plus bi corresponds to the coset a plus bx plus bracket g of x. And here the key observation is that as coset representatives, x squared can be replaced by -1, just like the complex number I squared can be replaced by -1. That observation led to the isomorphism between C and our quotient ring. And here's our punchline. As you'll read in chapter 34 of the textbook, the set of complex numbers C is not only a ring, but it is also a field. And therefore, our quotient ring, which is isomorphic to C, must also be a field. And here is a summary of our work today. We started with an unfactorable polynomial g of x, which equals x squared plus 1. And we concluded that the quotient ring r bracket x mod the ideal bracket g of x is a field. And so we have this implication. We showed that our quotient ring is a field by finding this beautiful isomorphism with the field of complex numbers. However, this isomorphism is very specific to our particular polynomial, g of x equals x squared plus 1 in r bracket x. So the question remains, how can we generalize? In other words, how can we generalize to show that an unfactorable polynomial g of x leads to the quotient ring being a field in all cases, not just the particular example that we worked with today? So we'll address this question next time, but that's the end of today's lesson, and so I will see you next time.